So far, we have learned entire computational procedure for matrix formation, operation, and solution steps for 2D case. Now we are going to extend our formulations to 3D. Now, what are the ways of doing it? So far, we have learned how to form our stiffness matrix, how to solve equations, and how to get the desired results, the unknown displacements, and the member and forces. Let's say we have a space frame, and how do we analyze it? One simple way of doing it is to use our 2D formulations for 3D frame structures. This can be done. All we have to do is break down the frame into a set of 2D frames. This can be done easily. For example, if we see this frame, we can break it down into a set of 2D frames such as frame number 1, which is in the XZ plane, frame number 2, which is also in XZ plane but just parallel to frame number 1, then frame number 3, this is in the YZ plane, and the other frames like 4, 5, 6 and 7, they are all similar to the frame 3. However, now if we see all the 7 frames, do we need to analyze all the 7 frames? The answer is no, because if we see closely, frame number 1 and 2, they are identical. So any one of them would be sufficient for the point of view of analysis and interpretation. Similarly, in the other direction, frames 3 and 7, they are identical. Frames 4, 5, 6, they are identical. Now what is the difference between, say, frames 3 and 4? The difference is with regard to the loading, the dead load from the slabs, which is higher in the case of the interior frames as compared to the exterior frames. If we want to see in detail how the vertical loads, they are divided, then this is how the division would be happening. And if we want to exactly draw frames 1 and 2, they would be having this kind of loading. So we can very easily analyze this set of frames by using the computational approach already learned. Similarly, frames 3 and 7, which are the exterior frames in the YZ direction, the loading shall be like this, and for the interior ones, the loading shall be double. Now how about interpretation? Now in the case of beams, we are getting the member and forces in the form of bending moments and shear forces, so we don't need any adjustment. However, in the case of the columns, a column is a part of generally 2 frames, so we need to superimpose the forces and moments for columns. For example, frames 1 and 2 span in planes parallel to global XZ planes, so their columns shall develop bending moments about global y-axis. Similarly, frames in the other direction, namely 3 to 7, they are spanning in planes parallel to global YZ planes. Hence, their columns shall develop bending moments about global x-axis. Similarly, axial forces also need to be superimposed. And same has to be done for the case of the foundations. When foundations are to be designed, accordingly the loads from the columns, they would be transferred in the superimposed manner. Here we are assuming that the role of the slab is only for distribution of the vertical loads. Alternatively, more rigorous way is to extend the 2D formulations to proper 3D format. Let's say we have a member inclined in any direction and we have to fix the global and the local coordinate systems as we had done for the case of the 2D. We assume the global coordinate system like this, that x and y axis, they are lying in the horizontal plane and z is pointing vertically upwards. As far as the local coordinate system is concerned, we have to fix the local x-axis along the centroidal axis of the member. The choice of the local y and z-axis lies with the user. Now, what difference will be there as compared to the 2D case? So let's see one by one. First of all, we'll find that at each end there will be 3 displacements and 3 rotations. For example, at the near end we have the displacements which are assigned the degree of freedom numbers 1, 2 and 3, And we have the rotations also, which are assigned the numbers 4, 5 and 6. At the other end, we have similarly the displacements 7, 8, 9 and the rotations 10, 11, 12. So that means our member stiffness matrix will be 12 by 12 now. The member stiffness matrix in terms of the local coordinate system. So what are the additional terms? So one additional term would be with related to torsion. We have the two rotations along the degrees of freedom 4 and 10, and they would give rise to torsion in the member, which was not there in the case of 2D. The torsion moment is given by Gj by L theta, where G is the shear modulus of elasticity and J is the torsional constant. Now what is theta? Theta is basically the relative angle between the degrees of freedom 4 and 10. So it is the relative or the differential angle of rotation along the axis of the member. Now the third difference would be with regard to the moment of inertia. Earlier all the members, they were bending in the xy plane. This action was invoking moments along the z-axis. Now there are two possibilities. Members can bend in two ways. For example, let us apply a force along the degree of freedom 2. So the member is bending, let's say like this. So this will generate a bending moment along the degree of freedom 6. Now the question is, which moment of inertia would be involved here? This particular moment is such that the moment of inertia along local z-axis will be involved. So accordingly, the bending moment will be, let's say, 6 EI z by L square, if we are imposing the displacement such that all other degrees of freedom, they are locked. Similarly, if the member undergoes displacement along the degree of freedom 3, in that particular case, the moment would be generated about the local y-axis, and here instead of Iz, Iy would be invoked. So this must be taken into consideration. Next, in the 3D analysis, we are assuming that the only role of slab is to transfer the vertical loads. We are totally ignoring the effect of the slab in lateral load distribution. Later on, when we go more advanced in the course, we'll study the role of the slab, how it plays the role like a rigid diaphragm aids in distribution of the lateral load. Now this would be our stiffness matrix in the local coordinate system. So we see there are 12 by 12 members, and here is the torsional term Gj by L. So J is basically torsional constant, and as a special case for circular sections, it is the polar moment of inertia. So you can derive this matrix by first principles. All you have to do is, just like in the case of the 2D, in order to obtain a particular column of the matrix, you have to apply a unit displacement along the particular degree of freedom and find out what are the forces generated along various other degrees of freedom. That will give you that particular column. Now here we can very easily observe that in the first column there are only two terms related to the axial force. Similarly, in the fourth column we can see that there is again the presence of only two terms involving Gj by L. So this is because in general the torsion, axial effects and bending effects, they are independent. Axial effects and bending effects, they were already considered independent in 2D analysis. In the 3D case, we have the presence of torsion. Again, our assumption is that we are considering 3D skeletal frames only. The role of slab is only for vertical load distribution. The slab does not offer any kind of stiffness. Now this is how we have to define our coordinate system. The local x-axis should be along the centroidal axis of the member. Here we have chosen the local z-axis towards the viewer. So accordingly, if we define or specify local x and z-axis, the third axis, that is local y-axis, results by the right-handed system. So we need to fix any two of them. The local x-axis has to be along the centroidal axis of the member, and then we need to specify any one of the local y or local z-axis. Once we specify that, we obtain the third axis by the right-handed rule. It's not compulsory that we always choose the local z-axis along the viewer. So it can be the other way also, that we fix local y-axis along the viewer, and then z-axis will be defined accordingly by the right-handed rule. The local y and z axis should be along the principal axis of the section. So if it's a symmetric section, then it's very easy. If the section is not symmetric, then there is a way we will see in the next slide. So after this, we come to coordinate transformation. We just recall that in the case of 2D, we had done simple coordinate transformation in terms of cos theta and sin theta, that is the direction cosines, where L1, M1 are the direction cosines of the local x-axis with respect to the global system, and L2, M2, they are the direction cosines of the local y-axis with respect to the global system. What is direction cosine? Direction cosine is essentially the cos of the angle the particular axis where the local axis makes with the global x, y and z axis. Same principle can be extended to 3D. Only thing is that we'll have one more term, direction cosines of local z axis. So let's see example. We have this 3D frame, and let's say all the members, they are prismatic and symmetric. So we can very easily choose the local coordinate system. Local x-axis is along the length of the member, and this is a beam element, so we may decide that local y-axis is vertical, that is it's coinciding with the global z-axis, and then the local z-axis comes towards the viewer and opposite to the global y-axis according to the right-handed rule. However, this can be other way also. Similarly, in the case of columns, we may decide that the local y-axis to be coinciding with the global y-axis. So for this particular member, we can define our direction cosines like this. For local x-axis, which is in the global x direction, so the direction cosines are 1, 0, 0, because it makes 0 angle with the global x-axis and 90 degrees with the other two. Similarly, for the local y-axis, which is coinciding with the global z-axis, the direction cosines are 0, 0, 1, and for the case of the local z-axis now, which is just 180 degrees opposite to global y-axis, the direction cosines will be 0, minus 1, 0. So minus 1 comes here because it's the cos of 180 degrees. So in general, we will have the transformation between the local and the global systems like this. So R is the joint transformation matrix. It is basically concerned with the 3 rotations or 3 displacements at the joint. Now here is the difference. In the case of the 2D, it used to be again the joint transformation matrix, but 2 of the terms were related to displacements and 1 term with rotation. But here the matrix R is either related to the 3 displacements or related to the 3 rotations. And then we can define member transformation matrix like this. It will be now 12 by 12 matrix. So the first R is concerned with the 3 displacements at the near end, 1, 2 and 3. The second R is concerned with the 3 rotations, 4, 5 and 6, again at the near end. And similarly, the third R and the fourth R are concerned with the displacements and rotations at the far end. Now, how do we obtain these direction cosines? So it's very simple for the local x-axis, because the local x-axis is along the centroid of the member. So the user must input the end coordinates of the member. So from the end coordinates of the member, using the principles of coordinate geometry, the direction cosines of the local x-axis can be worked out. So the unit vector along local x-axis will be like this in terms of the direction cosines. Next, for local y-axis, user has to give extra information, especially if the member is not symmetrical, and so the principal axis, they are not coinciding with the regular coordinates. So in that particular case, the direction of the local y-axis has to be explicitly defined. It can be done in 2 ways. Either a unit vector be specified directly, or the user can specify 2 points along the local y-axis, so that again using coordinate geometry, program can find out the direction cosines L2, M2, N2 for the local y-axis. So now we have the direction cosines of both the local x-axis and local y-axis. So once this information is there, then the right-handed system will work, and using the vector product, the direction cosines of the local z-axis, they can be worked out. Now, whether it's 2D or 3D, how do we analyze our building? If we give you either a 2D frame or 3D frame, now the real effect is that analysis and design, they are related. So when we are analyzing a structure, we have to fix some dimensions because we need to input the properties of the section in terms of areas and moment of inertia. So without fixing the dimensions, we cannot run the analysis. But the problem here is that at the beginning, we don't have the moments either, based on which we can fix the dimensions. So it has to be done either by thumb rules or based on some kind of experience. So first of all, we have to fix member dimensions tentatively. Once we have done that, then we can do structural analysis. And once we have the structural analysis, we'll get moments, axial forces and shear force. So we can check for the adequacy of the member sizes at critical locations. If the member sizes are fine, we take the analysis as final. If we find that the member sizes are either undersized or oversized, in that case we need to revise the member sizes and perform the analysis again. So it's necessary that if we are changing the dimensions, we must again analyze the structure, because now with change of the dimensions, the relative distribution of the forces and the moments would be different, so analysis would change. So again, after revising the analysis, we check for our adequacy again. So it is more or less an iterative procedure. So I hope that with this, now it's clear how do we carry out analysis in 3 dimensions. Rest of the procedure is exactly same. We have to form the KTS in the same manner, and after forming the KTS, we solve the system of equations in the same way that we have learned. So we'll just see one example in the interactive session immediately after the lecture. Thank you very much.